This presentation deals with the resistance of tapped blind holes based on experimental analysis. In the upper figure we see a typical bolt fitting being used for the connection of plates by a bolt and a corresponding nut. Regarding tapped holes or tapped blind holes, an internal thread is being fabricated into the structural steel in order to avoid the use of a nut. Such connections are being used in practical application in several cases. However, no specific information is given in Eurocode 3 with respect to the capacity of these connections. They are determined by the bolt itself, by the capacity of the bolt and the capacity of the external thread of the bolt, as well as the capacity of the internal thread in the structural steel, where the steel grade has decisive impact. The German National Annex gives certain information with respect to the necessary screw-in depth, M, which is to be considered in order to have the full capacity or provide the full capacity of the bolt. The figure on the right side exemplifies this screw-in depth with respect to the bolt diameter in dependency of different structural steel grades. It is well known that the approach of the previous slide, which is included in the German National Annex of Eurocode 3, may lead to quite conservative results. For that reason, the German National Annex also refers to a guideline VDI 2230, which contains a more sophisticated approach going along with more economic results regarding the screw-in depth. The guideline differentiates between two necessary screw-in depth, one for the tapped hole and the corresponding thread, and one for the thread of the bolt. Both screw-in depth are being determined, and the minimum value designates or defines the necessary screw-in depth for the connection to be able to transfer the full tension force of a bolt. In the lower figures you see the evaluation of these formulae for different bolt diameters and steel grades, and you see the corresponding necessary screw-in depth, which is going to be decisive regarding different steel grades of the structural steel. In literature we find another approach from Schwarz and Dose with respect to the necessary screw-in depth, and it is somehow different to the previous approximations in that sense that it doesn't differentiate between the internal and the external thread of the connection, but it defines a combined shear plane through both threads. Both threads influence the corresponding capacity, which is captured in the corresponding formulae shown right here. We see that there are different formulae for calculating the necessary screw-in depth, leading to totally different results. For that reason, experiments were performed at the University of Weimar in order to see how good these calculation formulae perform. In addition, the approaches so far only consider a fully loaded bolt. That is, if a bolt is loaded with the full tension force, the necessary screw-in depths provide that this tension force can be transferred by the connection. However, sometimes bolts are not fully loaded, and then of course the necessary screw-in depth can be somehow decreased. And these first experiments are supposed to give first insight into the dependency of the capacity of the connection regarding the screw-in depth. First, material properties were analyzed. The material properties of the specimens of the experiment, base materials of S235 and S355 were used, and corresponding tensile tests were performed in order to get the material behavior. In these first experiments, bolts of steel grade 10.9 with diameters M12 and M20 were also used, and these bolts were tested with respect to the tension capacity of these bolts. After determining the material properties experimentally, the actual tests on the tapped holes were being performed, and you see the specimen set up on this slide. The specimen consists of a base plate in which the thread is manufactured and a bolt which is screwed into that base plate. At the bolt head, an additional plate for load introduction purposes was placed. In order to have a clearly defined screw-in depth in the individual tests, part of the bolt thread, which does not fully contribute to the capacity, was removed as shown on the right side of the figure, and in doing so we were able to calibrate the screw-in depth in the experiment very well. The test specimens were set into a testing machine afterwards. For that purpose, we designed a corresponding mounting device which we could use to arrange the specimens quite well in the machine and then perform the tension tests. Depending on the screw-in depth, we could observe different failures of the bolts and the threads. Here exemplarily you see in the upper figures sheared off and deformed external thread and internal thread. In the lower figure on the left side, a very strongly deformed thread, and on the right side the rupture of a bolt. In the upper pictures of this slide, you get an additional impression on the failure modes of the sheared off external and internal threads. These failure modes usually occur when we have rather small screw-in depth, while the lower pictures show the fracture of the bolt, where we observe rather straight fractures when we have big screw-in depth, and with the decrease of the screw-in depth, the failure surface tends to have a diagonal orientation. We observed that the failure of the bolt usually occurs before reaching the maximum tensile strength of the bolt that we determined in the previous experiments. In this table you see the results of the experiments summarized in a table, where you see in the left column the different bolt and steel grades applied in the different tests. The middle column represents the screw-in depth, and on the right columns you see the strength tested, the mean value, the standard deviation, since for every configuration 5 tests were being performed, and on the very right column you can see whether the thread of the structure failed or whether the bolt showed a rupture. Afterwards, the experimental solutions were plotted in such diagrams as you can see here, exemplarily for the configuration M20 10.9 and a structural steel of S355. The blue dots represent the experimental results showing a thread failure, while the red dots show the bolt rupture. And you see that when we get higher screw-in depth, the failure tends to stronger to a bolt rupture, while for lower screw-in depth we rather have thread failures. Next to the experimental results you see black dots of different shapes representing the different calculation approaches for the screw-in depth, and we see that obviously in this case Eurocode 3, the national annex, is quite conservative, as it determines much higher screw-in depth necessary for full transfers of the force, while the VDI guideline tends to underestimate the necessary screw-in depth for different forces. Even though tolerances which are not covered in this plot right here were considered in the calculations as well, and they show the same tendency. So when we use the VDI calculation formulae and include corresponding tolerances in these calculations, then still VDI guidelines underestimates the screw-in depth in comparison to the experiments we performed. We see that the results of Schwarz-Dose tend to fit to the experimental results best in this case. Summing up these first experiments, we can see that the German National Annex seems to overestimate the required screw-in depth, while VDI guideline 2230 seems to underestimate the values, being on the unsafe side then, and we need additional investigations here to clarify these things. The approach of Schwarz-Dose tends to correspond to our experiments best, and it seems to be most promising in this context. With the bolt rupture, we observed sometimes diagonal fractures of the shanks, and even we didn't reach the full tension force, tension capacity of the bolts when it came to the rupture. We need additional investigations here for clarification as well. It could be the effect of the pitch of the thread leading to an unsymmetrical force transmission, and if we have smaller screw-in depth, this impact will become stronger, leading to additional stressing in the bolt shank, but we have to clarify these things. That means for the university valid conclusions, we want to perform further experiment and also add numerical investigations as well. For that reason, of course, we want to continue that research at our university. We want to find a formula with which we can determine the necessary screw-in depth depending on the bolt load which has to be transferred in a connection. Thank you for your attention.